Okay, this is 1D Kinematics problem set review. I'll be moving quickly through these because we have the ability to pause the video, slow it down, and hopefully I remember to put the timestamps in the description. So 3, you can read the problem yourself. We have a runner that's moving in the positive direction with different accelerations. It's very important for us to be able to separate this into different phases of motion. My first graph on the left is position versus time. Then in the middle is velocity and then acceleration. Okay, so after reading the problem, I see that I have 3 phases of motion to consider. One where the runner is speeding up from rest. So I have something like this. It's curvy, quadratic. Second phase of motion, in my position time graph, I have constant speed, something like that, all the way up to the end of our second phase. And then we have slowing down until stopped, so we go flat. Okay. When I put that onto my velocity time graph in the middle, I know I have a 0 velocity to start, increasing to some value, which is the final velocity at the end of phase 1. It goes constant. And then we have a sharper descending velocity at the end because we have a greater magnitude acceleration when we're slowing down at the end. For acceleration, remember, look at your slopes. On velocity, slope takes you to the right. I can see my first slope is positive over here in the first phase of motion. So that means I'm going to have a positive value for my acceleration. Then in the second phase of motion, on velocity, it is flat, 0 slope. It means I have 0 value acceleration. And then in the third phase, I have a much steeper but negative acceleration, so it should be down here. Let's label these parts of motion 1, 2, and 3. Our question is asking us to find the total displacement. One way is to find the total area under the velocity time curve. We'll also show that we can just write all the things that we know about each phase of motion. So there's phase 1. These do not correspond with the graphs. I'm now doing the analytical part, the math part. Those are my phases down here, phase 1, 2, and 3. So I could think about all the different things I could know, my 5 kinematic variables for each phase of motion. Time, acceleration, and then let's see if I can just copy this quickly. No, because I'm recording. Okay, that's fine. We can do this for each of our 3 phases. We want to note that the end of phase 1, we have a final velocity, which will be the initial velocity for phase 2. In each of these phases, we have a different acceleration. As we can see on our acceleration graph, we have a positive acceleration to start. You can put that in phase 1, 0.5 meters per second squared. And look at the acceleration graph. In phase 2, the acceleration is 0. In phase 3, we read the question, we'll note 1 is the magnitude, but it's -1 as we put in our graph. We're moving in the positive direction the whole time and slowing down in phase 3. So that needs to be a negative acceleration, opposite direction of motion. I know in phase 1, my initial velocity is 0. Final, I don't know. Displacement, I don't know. Time is 12 seconds. And I can even add that onto my graph to help me know better how to map out the problem. Phase 2, I have an initial velocity, which will be equivalent to my final velocity from phase 1, but I don't know it. We're moving at constant speed in phase 2, so VI and VF in phase 2 will be the same value. So you could just call that V and just have one of them written there. Delta X, we don't know. Time, we do know, that's 18. So I know I go from 12 to another 18 seconds is now 30. That's helping me build more information into my graph. Notice in phase 2, I have 3 unknowns. That's not a good spot to be in. I want to usually know 3 things at least. Phase 3, initial velocity, I don't know what it is, except that it'll be the final velocity from phase 2. Final velocity we do know is 0 in phase 3 because we come to a stop. Delta X we don't know, time we don't know. So also in phase 3, we only know 2 things. Okay, so notice in phase 1, we actually do know 3 things. That's a hint that that's the place we need to start because we can actually figure out more of our information. Though the question's asking about delta X, I could find that first. Let me go ahead and do that, I guess. Delta X in phase 1. I got to think about what equation is going to be useful for me here. I have initial velocity, time, acceleration, and delta X. So maybe I go to equation number 2. Okay, so there's delta X equals VIT plus 1/2 AT squared. I know the initial velocity is 0, so I simplify this. to be 1/2 at squared, which means I have 1/2 times 0.5 times 12 squared. That means I'm going to have 144 over 4, which is 72 minus 36. Right, because 72 times 2 is 144. So there's delta x for the first phase of motion. For phase 2, I don't have enough information to go on. And look, I can amend my list for phase 1 to include my new value for the displacement of 36 meters. I now have enough information that I could find for phase 1 what the final velocity is, and that'll help me with determining delta x for phase 2. So let me come here real quick and just do final velocity for phase 1. Okay, so that's going to be, well, I could use this first one. Initial velocity is 0 plus I have an acceleration of 0.5, so 0 times time, which is 12 seconds. So my final velocity at the end of phase 1 is 6 meters per second. All right, so I can put that up here as my values here, because after the end of phase 1, phase 2, I have the same constant speed the whole time. So there it goes. And this also can go in for my VF over here, 6 meters per second. Now we figured out some more stuff for phase 2. I'm running out of room, so I'm going to bring more phase 2 work over here. This was all for phase 1. All right, so for phase 2, I want to get to delta x, and I have all my other information. I'll just go with equation number 2 again. This is super useful. And we can point out that our acceleration is 0 here, so our equation just becomes v. Initial and final are the same. Velocity times time will give me my displacement when I'm moving at a constant speed. So let's go ahead and put in our velocity there of 6 meters per second, and our time is 18 seconds. 18 seconds. Okay, that's 60 plus 48 is 108 meters. Okay, so now I found the displacement throughout phase 1, and I've found the displacement throughout phase 2. So that means right here on my graph, this is, I just forgot the number, 36. We want to see it visually, because this is position versus time. And at the end of phase 2, which is right here, we've traveled another 108. So that's 126 total. And then phase 3, we need to find out, and then we'll be able to get our final displacement and figure out what our total displacement for the entire trip is. So here in phase 3, we now know that our initial velocity is going to be our 6 meters per second. Looking at my velocity graph helps me recognize that. Excuse me. And now I can find my delta x if I use an equation that doesn't have t in it. So I think I got one right here. Because we know our final velocity is 0. So final velocity is 0. Pop that in there real quick. We got vi squared plus 2a delta x. Okay, and I want to solve for delta x because that's what my question is asking. Let me get the total displacement. So I got minus vi squared is 2a delta x minus vi squared over 2a is delta x. So minus v initial, vi, that was our 6 meters per second. That's going to be squared. Over twice our acceleration, so I have 2 times minus 1 is delta x. All right, and then those minuses are going to cancel out. Hope we can see that. And so I'm left with 36 over 2, and this is going to be meters squared per second squared, if you really want to see all the units. We know displacement delta x should be in meters. All right, so that's 18 for phase 3. And so our total displacement, let's call it delta x total, will be our 36 plus our 108, which gets us to, wait, what was the first one? Oh, the first one was 36. Why did I put 126 up here? I thought the first one was 18. I'm losing it, guys. 108 is 144, right? Okay, and then I'm going to forget to edit that. What is the last one? 18. So then 144 and 18 is 162, right? 162. Keep going. All right, so 162 meters is our total value for our displacement there. Just looking at each phase of motion, we can find list of things that we know, use the graphs to help us, and then we can get a total value for the displacement. I think that's all we needed to do there. Yep. 4, this is like throwing an object up into the air. So here's T. Let's get these out here quick. PVT. PVT. So in this one, our ball starts with a high velocity. I'll do the velocity first. Rolls up the ramp until it stops for a moment, and then it comes back down. So this is, imagine, you can also imagine throwing a ball up into the air. All right, 2 main phases of motion here. Okay, so my position is high speed, then stopped. So it goes flat, and then coming back down, like so. And acceleration, I can look at my velocity. I have a constant negative slope. So I have constant negative velocity. Acceleration, excuse me. I have a constant negative slope on the velocity. Therefore, I have a constant flat horizontal negative valued acceleration. Okay. We're just going to look at this part because part 2 of this is for the using the equation from our ramp lab. Okay, but we don't really need to worry about that right now. So I can just look at one phase of motion here since I'm trying to figure out what is VI. Okay, that VI is unknown. And so what we mean by that VI, if we look at just the first phase 1 of the motion and not phase 2, VI is here. We can see that it is not nothing. It is some positive value, just like you throw a ball up into the air. And then VF for the first phase of motion is up there. So that is VF, and that is 0 because it stops for an instant. So that's something we know. We don't know the acceleration. It's not little g, it's a ramp. Okay, the ramp would have to be perfectly vertical for your acceleration here to be little g. All right, so this is not that. And you think back to the ramp lab, your acceleration on the ramp was not little g. It was like 0.5 meters per second squared. All right, our time we have is, I've forgotten, 5. Yeah, okay, 5 seconds. And our delta x, distance along the ramp, or displacement along the ramp here. In my graph, I'm calling up the ramp positive. That's why we move in the positive direction in phase 1. That's 10 meters. And here I got enough information. I just wrote acceleration is 0. That's wrong. I'm sorry, question mark. Another edit I'm going to forget to make in the video. Okay, acceleration we don't know. We don't know, right? It's not little g. We don't know what it is. We definitely have it. It's a constant negative value, as we can see in our acceleration graph. Okay, so I have v final t delta x. I can look at my kinematic equations, and if I don't have acceleration, but I do have time, I'm probably going to go with this one. 1/2 initial plus final times time. Okay, I have something that's equal to 0. That's my final. So I have 1/2 times VI times t. I want to find VI, so let's isolate VI. Twice delta x over t is VI. Now let's substitute twice 10 meters. All right, so I got meters upstairs over a time of 5 seconds. So now my total units are meters per second. Sounds good. 20 meters per 5 seconds is VI. 20 over 5 is 4 meters per second is VI. Okay, 6. Let's take a look at 6. Once again, let's get our graphs going. This is one of those questions in which we have a collision or an intersection of two objects. They meet each other and occupy the same position in space. When you have two objects, you should be writing equations for each object and drawing graphs for each object. I'm going to have 2 sets of graphs there for you if you get 2 objects. Hopefully I remember to do that. Here I'm going to do cart A in red, and then put an A there. And we get cart B in blue. Okay, there's cart B. And then we have velocity. B is a constant negative value here, minus 2.2. And cart A is going to be constant positive velocity closer to the x-axis. Okay, and then we have for acceleration, nothing. There's 0 because they're constant speed. Okay, and so we're trying to see where they're going to hit. We know it should be somewhere between 0 and 6 meters just by looking at the velocities of each of these guys. Okay, and I'll show a couple ways to do this. One, you guys are going to be like, oh my gosh, why didn't he just say that? But it's better actually for us to consider writing an equation for each of these carts. So consider for a moment here that we have just the position versus time graph to look at. And your go-to equation, if you are going to represent the motion as you see it on the position time graph, is to be using the second kinematic equation, which is this one, because it tells you everything about the position. This is how you would actually graph the position graph. We would separate our delta x into x initial and final, bit plus 1/2 at squared. And then we would isolate the final position, because that's what we're looking for, is the final position of these carts is right here. That's where they will meet. This is true for the next question and for question 9. Can also be used for question 10. So I have VIT 1/2 at squared, excuse me, plus initial position. Okay. Now, this is quadratic here, but let's pull it back for a minute. Excuse me, let's pull it back and think, okay, look, we're looking at these red and blue lines on the position time graph. These are just linear functions. So if you don't have any acceleration, this y equals mx plus b will represent those linear functions, the red line and the blue line. Let's look at our graph here. Blue up at the top, this is the initial position of cart B, the blue one. And down here at the bottom, I have right here the initial position of cart A. They both share the same final position, right? The final position of A equals the final position of B equals what I can just call x final. And we care about that because we're told they collide. If, like in the next one, a car catches up with the truck, they're going to occupy the same final position. Same with the basketballs, same with the very last question. They occupy the same position. So this is an important piece of information to look at. We have two objects, so if we write an equation for each object, that'll be an equation here for our red line and an equation for our blue line. We can solve that system of equations for something like the time, right here, that t final, or we could solve it for x final, and we will know where they are. So we want to have an equation for each of our objects. So check this out. For blue, y equals mx plus b, well, on the y-axis, we have our final position. So this would be x final for blue, cart B. The slope m is the velocity of the car. The slope on position time is the velocity. Remember, slope takes us to the right. So the slope on the position time graph is the velocity. Steeper means faster, right? So this is telling us the velocity of cart B. It's constant. We don't need initial and final if it's going at a constant speed. X in y equals mx plus b is whatever's on the x-axis. That's like your input variable, right? That's time. Plus b is the y-intercept. So we can see that up there for the top of our graph, the blue line is at x initial position for b is what we would have for a y-intercept. For our red or cart A, I would have the same looking thing. X final position for A is going to be the velocity of A times time plus the initial position of A. You have the values for those. You plot them into a calculator on Desmos, a graphing calculator, right? Then you will see the actual graph that I've drawn for position versus time. And you can click on it, like in Desmos, you can click on the intersection and check your work and see that it actually represents that. All right, so let's put some numbers in here, I suppose, though you could continue to use variables. I'm just going to call this, continue to call it final position of B. Velocity of B, we've got to be careful, it's minus 2.2 t. And plus 12 because it's starting at an initial position of 12 meters. And then we have x final of A. Velocity of A is 1.4 times t plus 0. So let's just get rid of the 0, eh? Okay, now you have two equations and two unknowns, right? We don't know what the final position is. We don't know t. This is why we need a second equation. Okay, this is why you have to be able to solve systems of equations, because sometimes there's more than one unknown thing. I keep writing t. Question mark here. All right, so my friends, what you got to do is decide how you want to solve this system. Because with all these collision problems, we often have x final isolated. It's convenient simply because the final positions are equal to set the other sides of their equations equal to one another. For two things being equal to another must also be equal to themselves, each other. So here we go. We're setting the right side of our equations equal to one another. I've got 12. Did I copy that down right? Yeah. 1.4 plus 2.2 is 3.6 t. So I've got 12 over 3.6 equals t. I think the time here should be about 3.33 seconds. And then the position, the final position where they intersect is 4 point something. Y'all, I don't remember exactly, but something like that. Once you get the time, you just take that time and put it back into this one. I can't pull up the calculator on my computer right now because I'm recording, but that's how you can get the final position. Okay, think two objects. Let me get two equations. Let me model the position versus time graph with equations. All right, 6. Similar thing here. Let's make sure, I really think drawing the graphs is the best way to start. Everything is going to be positive here, so we'll just do that. AVT, VVT, PVT. We're going to do the same thing as before. I'm going to have a truck that's moving at a constant speed, so it's going to be linear. Okay, so it's going to look like that. It's going to have no acceleration. It's going to be down there. Okay, that's our truck. In red, we've got our police car starting from rest and speeding up. Whee! And then it crosses over here, right? Just like the previous question, that's where they're going to have the same final position. There's X final. It's going to be the same for red and blue, so I can just call it X final. The police car has a 0 velocity to start and increases. It does need to be moving faster than the truck's 25 meters per second in order to catch it. Okay, so, oh, and I need that acceleration for the car. All right, so let's think again. I have one equation, y equals mx plus b, that describes linear trends, and that's certainly what I have with the truck in the position time graph. And then I got curvy business going on with the car that's going to be quadratic. Anytime we see a curvy graph on position, it's going to be quadratic. It's going to be squared. It's not going to be some other crazy exponential thing. And that you are familiar with seeing as y equals ax squared plus bx plus c. Okay, so when we say, oh, it's linear, for our graph here, remember x-axis is time, initial position of the truck, call it that, is 0. Initial position, this is rather convenient, of the car is 0. They're starting from the same position. We can see that right there, right? Okay, so what we do with our y equals mx plus b, we have, okay, what's on the y-axis? X final of our truck. We have our slope of our truck. Remember we said slope here when we're traveling at a constant speed. M, the slope, is the velocity. So that's our, let's just call it initial velocity of our truck for now, multiplied by time, because that's what's on our x-axis, plus the final position. I'm sorry, the initial position. The initial position is our y-intercept, right? B is y-intercept. So look, that's just going to be x initial of our truck, which is going to be 0. And let's go ahead and put some numbers in there for that. X final for truck. X final for truck is initial velocity of truck, which is 25. T plus 0. Okay, plus 0. I'm not going to write. Okay, so there's our equation for our truck. Let's go over here for our, police car. Okay, the car now has quadratic. So how are we going to make it look like the quadratic equation that you are familiar with from math? Well, on the y-axis, and this is we're looking at the position graph here. I know I wrote it under the velocity. That's not what we're doing. Looking at position here. That's where you see a quadratic function is on position. Okay, y is again the x final, but now I'm talking about my car. The a parameter is 1/2 the acceleration. How do we know that? Calculus. So just look at, not calculus, look at this. Remember our equation here from the second kinematic equation is 1/2 at squared. All right, this is just a quadratic function, but the a parameter, a always comes in front of the squared component there, the x component in this formulation, in the standard formulation of the equation. Okay, the a component is in front of x squared. Well, in our kinematic equation, it's not x, it's t that is squared. Okay, so 1/2 a is the parameter or the coefficient that comes in front of the squared variable. So here's 1/2 at squared plus bx would be like initial velocity times time. So initial velocity is the b. So here's vi. All right, that's the b parameter. Draw an arrow over to the b. Times time. And the c, where's the c go? I don't see any, like where c would be over here. Where is it? It's inside the delta x, because delta x is actually finest minus initial. So if you add the initial position and you get it over here, then that's what the c is. It is the initial position. That delta x can be written like that, because delta x means change in position, x final minus x initial. So this is our quadratic function from the kinematic equations. We've just reordered it to put it in the order of the way you expect to see a quadratic function, with the highest order term first, that's the t squared, then just the t, then the constant. Okay, so if we do this for our car, we've got x final. Car is ready for numbers now, so I'm going to put in 1/2. What is its acceleration? I don't know. 5, I think. Oh yeah, 5. Okay. I don't need parentheses here. Get out of here. Let's do 5 meters per second squared. I really hope the microphone is working. I'm not doing this again. VI is 0, right? VI is 0 times t. So we don't even need to write it. Initial position is 0, so we don't even need to write it. So just get rid of those zeros. Done. Right? 0 times time is 0. So here is the equation for our truck that we care about. Here's the equation for our car. And once again, like before, we say, wait a minute, their final positions are going to be the same, because we care about when they have the same final position. When does a car catch up to the truck? So we'll set these two things equal. We get 25t equals half of 5 is 5 halves, or 2.5, and that's t squared. And then we lose a t here, we lose a t here. So we've got 25 over 2.5 and equals t. And so we've got 10 seconds for our time for them to intercept or get to the same spot. All right, 8 can be helpful to draw a picture here. Say we've got 2 people, one person's in a window here or whatever, and one person is up here. I forget who is who, but you have one water balloon, okay, that is being dropped from this height, which is, I believe, 30 meters. So if you call down the positive direction, which would be perfectly appropriate for this one, you'd have positive, and for this guy, delta y would be, I don't know what it is, 12. So those two different heights. So this one, if we have, we want to look at the time in between each balloon hitting the ground, then I'll do it for Mark and Whitney, I think are their names. Mark is standing at 12 and Whitney, so he's at 12, Whitney's at the 30. Okay, so I could find an equation that is relevant. You can list the things that you know. 1/2 AYT squared. In this case, our AY is little g, acceleration due to gravity, 1/2 AYT squared. All right. And so for Mark, I have both of them have an initial velocity of 0. So that's important to put the 0 in first. So I have 1/2 acceleration. Here's little g. It's not the Iron Man with the rocket pack, going and having a 50 meter per second squared acceleration. There's no mention of any other forces or anything. Free fall conditions apply. Then you just have little g. So there's 1/2 gt squared. See, for both of them, the equation's the same, right? We're looking for the amount of time in between their impacts hitting the ground, which means we need to know how long each one takes to hit the ground. So we'll solve for t. I'm doing that right now in one step because, why not? Multiply by 2, divide by little g. That equals t squared, so take the square root. Okay, so see, same equation for each one. Now I just have to be careful because for Mark, I have 12, and little g we're using 10. I'm calling down the positive direction for my own convenience. If they only ever move in the positive direction, if they only ever move downwards, then it's often more convenient to just call down negative. I think 30 was the other height, okay? So here I've got the square root of 24 over 10 is 2.4 is time, and here I have the square root of 60 over 10, so the square root of 6 is time. So you need to subtract those. I don't have my calculator right now, but I would do square root 6 minus square root 2.4. I would turn these into decimals first, and that would be the time in between impacts, which is the question. How much time basically after the first one hits does the second one hit? I believe that is 0.9 seconds. I forget, honestly. Okay, but that is how we work that. Graphs, I'm not doing graphs for that. All right. Question 9. All right, this is another one where we have, and it looks like I have the work over here. I do. Look at that. There you go. We have objects that will be occupying the same position. We will do graphs for this one. Real quick. Here's position, here's velocity, here's acceleration. Let's call the top one the blue one. So the blue one starts at the top from rest and speeds up as it falls. Okay, so that's going to be quadratic, even though it doesn't look like it. That is quadratic, squared, right? And then it starts, you could also put, this is the 80 meter position right at the top. So that's the y initial of the top ball, t. The initial y for the bottom ball is right, theta, which is 0. And we're throwing that upwards, so it's got an initial velocity, but then it slows down. It would come to a stop and continue to come down. I'm not drawing the best graph, to be honest, but who cares, because what happens is they collide, and they're going to collide right here, this is just like our previous ones. Remember, first it started with two carts moving at a constant speed. They were both linear. Then we had one that was linear, the truck, and the other car was parabolic, quadratic. Now they're both quadratic. See, it just gets a little slightly more, whatever. Okay, so we want to find that final position. Notice I've done the same thing here. I know I have two quadratic functions, this one for the top ball, this one for the bottom ball. This is a y right there at the bottom ball. Okay, and then I'm just setting them equal to each other. Whoops. And the solving for my time, I set them equal, solve for my time. I got to remember to put in the 80 for my initial position of the top one. Check out my 1/2 GT squares, just go away. So really it's this is all you need to know, which is pretty cool, I think, because all you need to know is the height, sorry, this is a weird T, the height that the first one is dropped from, and the velocity of the bottom one, to figure out how long it takes before they collide. So at 3.2 seconds, you just take that and you put it back into one of your equations that's got time in it, and then you can get the position. Okay, and you can double check, you put it into both equations and make sure that you're getting the same final position. Let's take a look at our velocities. This one's moving down, I need a negative. All right, so blue starts at 0 and constantly increases its negative velocity till impact. And red starts with a high positive velocity and comes down like so. It should have the same slope because they both have the same acceleration, which is little g. Oh, check it out. Red and blue make purple. Get it? All right, next one. 10. Okay, in this one, Richard Branson is, I forget why, has to abandon the balloon. So his VI is 0. Well, let's keep him red. We don't want him to hit the ground. We want our safe rescue drone to catch him. So his delta Y, if we call down, let's just call down positive for him. This is going to be his delta Y right here. Down is going to be the positive direction. So his delta Y is going to be equal to 700 minus 250, which is 450, right? So he's not going to go 700 meters down. That's death. We want him to be caught by the drone. The drone, which we'll put in blue here, needs to make it this horizontal distance, all right, which is its delta x. It's moving horizontally, okay? So the drone doesn't have gravitational acceleration making it speed up in the horizontal direction. That's no. It's going to have just its 5 kilometers or 5,000 meters it's got to travel. All right, if it moves at 200 meters per second, it's not going to make it in time. That's its VI. That's its VI is 200 meters per second. Currently, it's 5,000 away. So we need to figure out what the acceleration of our drone is going to be. So I could have like drone over here in blue. Let's do drone over here in blue. VI is 200. VF, I don't know. It's going to be something. I don't really care. I care about its acceleration necessary. The time it's going to spend traveling that 5,000 kilometer distance, I don't know. Delta X is the 5,000 meter, 5 kilometer. 200 meters, there we go. And then Branson over here, poor Richard, he has an initial velocity. He's going vertically, right? And I called down positive. Drone's going horizontally and call to the right positive. This is really good to do what I just did with those arrows by each one, because with projectiles, you definitely want to do that. Okay, his VI in the Y direction for Branson is 0. VF, I don't know. I don't particularly care. His A is little g. We're calling down positive, so it's going to be 10. Time, I don't know. His delta Y is the 450. 700 minus 250 meters. Okay, you can look at these. Which of these has at least 3 known things? Branson. Boom, boom, boom. Okay, we got to think about, well, what's worth finding out? You could find VF, you could find T. It's more important for us to find T, because if we can figure out the time it takes for Branson to get to this position, which is where the drone needs to get to, if we find the time it takes for him to fall to that position, 450 meters down, that will also be the time required of the drone to move the 5,000 meters horizontally, so we can use that time over there for the drone, which is exactly what we'll do. So let's see, Brandon is falling from rest. You know, it's going to be the same as Mac and Whitney's balloons, excuse me. Same as Mac and Whitney's balloons. All right, in the whole equation, for funsies, it's starting from rest, so we just have 1/2 acceleration in the y, which is g, t squared. I want to find time, so it's going to be this, twice delta y over g square root. There we go. Now the time we've got is square root twice 450 over 10. So that time is going to be square root 90, right? Because we got 2 times 450 is 900 over 10 is 90. Square root of that is 9 point something. 9 point something. I don't know. Put it in a calculator. All right. Or wait, we could do, we could do square root 9 times square root 10. So we have 3 square roots of 10 seconds. Or whatever. I'm going fast because I gotta hurry up. All right. So that's the time. We now know it. So we can put it in 9 point some other numbers over here with our time for our drone. And our drone, we have initial velocity, we're going to have time, we want acceleration, we have delta x. Look what equation is coming back. How useful number 2 is, huh? All right. So we want to find acceleration. Well, maybe I don't want to use this one. I mean, I guess I could. Delta x minus VIT over a, I want a t squared, but then I got to distribute this too. Maybe I should actually show that I'm doing it. Okay, first step, like this, 1/2 a t squared. Then I'll multiply by 2. I want to get a by itself. That's what we're searching for. Okay, so I got 2 times delta x. Make sure you're multiplying the whole left side of the equation by 2. That means put some parentheses on there or distribute it. Over t squared equals a. And then delta x is our 500. Initial velocity, 5,000, my bad. VI is the 200 meters per second. T is going to be our 9. I'm pretty sure it's 9 point something, right? Yeah, because it's square root 90, yeah. 9 point something. I don't know what the other after the decimals will be. And then t is also the 9 point something, right? Just make sure you square it. Our a should be approximately equal to 68 meters per second squared. I forget the exact number. 60 something, I know that. 11, Tony's on the ground. He needs to make it to the top. Okay, so we got 2 phases of motion here. Important. He does start from rest. That could be a little clearer in the description of the problem, but that's what I meant to say. Starts from rest. 2 phases of motion because we have 2 different accelerations. We have an acceleration from the suit, but then the suit turns off, and then he's in free fall conditions. So I said free fall conditions in the problem. That means that the acceleration is little g. So here he is. He's starting from rest and speeding up. He achieves some, I don't know, final velocity. That's whatever it is. And then the suit's engines turn off and he's just coasting in free fall. He continues to move, but he's slowing down because gravity's slowing him down. And he reaches some max height up there, right? So that would be his max height because this is vertical position. This is a y versus t graph. His velocity is increasing. And let's make it dramatic. We'll say it's increasing, quite a bit. And then he's slowing down. It shouldn't be as fast, okay, but I'm going to run out of space. But eventually it would get to 0 because gravity's slowing him down. I should have made I would need a longer VT graph to show all that. Okay, but his acceleration is very high positive value here, and then the acceleration due to gravity in the second part, because he's in free fall conditions, which we're going to call minus 10 because we're going to call down negative here, that would be closer to the x-axis. Okay, so we might say, okay, done with graphs, 1, 2 phases of motion, and I can list my stuff. I've got an acceleration in the y direction that he has, time, v initial, v final, those are in the y, and delta y for part 1. So his acceleration in part 1 is 50 meters per second squared. Time is 3 seconds. Initial velocity is 0. Final unknown. His delta y unknown. Okay, in the second phase of motion, we have an acceleration in the y direction that is little g. We're calling down negative, so it's minus 10. All right, then we have a time, which is unknown, and an initial velocity, which is unknown. I'm just going to put everything unknown here. We don't really know anything else, right? Like, we're trying to see if he makes it to the 1,300 meters total to get to the top of the building safely. So we look at phase 1 is the only phase where we can figure some stuff out. So like for delta y, if we wanted to find that, because we're trying to see how high he goes, we could say, all right, what do we know? A, t, VIY. Guess what equation is going to come back up again? VIYT plus 1/2 AYT squared. So he had an acceleration that's speeding him up. So the acceleration and the velocity are in the same direction. So that acceleration is positive. So delta y, initial velocity is 0. So we just have this. We already solved for delta y. So I can say this is 1/2 times 50 times 3 squared. So that's going to be 9 times 50, right? I should put it in order. I'm taking half of 9 because 3 squared is 9, which is 4.5 times 50, or I can do 25 times 9, whatever. Either way, it's 225, right? Okay, now I'm back. Where were we? Okay, so we have the displacement from the first phase of motion is 225. That tells us a little bit about how far he's traveled. Now we need to get to the second phase of motion. I'm put in my 225 over here because now we know it, 225 meters. In the second phase of motion, we have to think about how can we figure out whether he makes it to a total height of 1,300 meters. And one way we can do that is recognize that at the maximum height, at max height, we know that's right before he turns around and starts falling back down. So at max height, v final in the y direction will be equal to 0. Right? So we could say, okay, let's say that his final velocity in the y direction is going to be 0. Now we know another piece of information that can help us figure out our question, because we want to use v final in the y direction as 0 so that we get the maximum height. And we're asked if he makes it to the 1,300 meter mark. So we need to know how high he's able to travel. So this will give us a maximum height. If he travels to a max height that's going to be higher than 1,300, then we know he has made it to the top of the tower. We only have 2 things known so far in phase 2, little g and this v final in the y direction. So what we're going to do is have to figure something else out. If we look at our graphs, we know that our initial velocity for phase 1 was 0. The final velocity in phase 1 is right there, and that is also the same as the initial velocity in phase 2. You've dealt with that before. So what I'll do is find v final. We'll find v final from phase 1, and that's not too difficult. I have initial velocity, which is 0. I have acceleration, time, these are all in the y direction right here. And so v final in phase 1, v final in the y direction is going to be 0 plus his acceleration is 50 meters per second times a time of 3 seconds. So his final velocity in phase 1 is 150 meters per second. That's pretty quick. Okay, so that is now something else I know about phase 1 of the motion, and that means that the initial velocity in the y direction for phase 2 is that 150 meters per second. Right, now I know 3 things. Now we're cooking. So I want to find out what delta y is for our phase 2. This is still phase 2 over here. Okay, so how far does he move in phase 2? vertically speaking. So this is the one the engines are off on its suit, and it's just the acceleration in the y direction equal to little g. It's free fall. I notice I have vi, I have vf, I have a, and I have delta y. So that points me to this equation here. V final squared is v initial squared plus 2 times the acceleration times delta y. I have to be careful. I'm calling up positive, which means I'm calling down negative. I can even write that in as a symbol like I did before. That can be very helpful. So final velocity is going to be 0. Right? We said that's going to help us figure out his max height. So we're going to just put our 0 in first. A, y, delta y. Acceleration of the y is little g, so I'm going to actually just put that in there right away. And delta y is what we're looking for, so we'll isolate it. So I've got minus vi squared is 2g delta y. And then I've got minus vi squared over twice g. And then I can substitute stuff in. I got minus, initial velocity is 150 meters per second. And it's going to be squared over 2 times minus 10 meters per second squared. This is delta y. And then we're going to get whatever our answer is. I believe, I forget what it is. I think it's 1075. You guys, once you get the numbers in there, you just calculate it. I just don't have my calculator and am not much time left. So I believe that is correct. I think so. That would be our total delta y. We'd have to add these two together, right? There's from phase 1, from phase 2. So delta y total, the total maximum height he can get to should be no, that's not right. I don't know, I can't do that right now. I don't know exactly what that value is. You put it in the calculator. Do I even have my phone? No, I don't even have my phone. So, well, let's see. We could have, I know it should be 1350. I'm just going to say that. Sorry, I'm going to rush. I don't have time to do calculations. All we care about, variables are more important than the calculations. His y total should be around 1350, which means this should be 1175, right? Because that's plus 2. No. 13. Yeah, 1315. 1125. That's what delta y should be for number 2. Because we got 1125. I know the answer is 1350, so we add our other 225. So there's 1, 3, 25 and 25. That's 50. Okay, so this one should be 1125. If not, I know this is the final answer. All right, the last one is the hard one, where, again, starting with the position, and we have intersecting objects that end up occupying the same position. Let's change that a bit here. There's ABT, BBT, PBT. Computer is overheating now. So you have Tony who gets thrown out. This is from the like 1300 up here at the top. Computer is very hot. I can barely put my hand on it. All right, so Tony is getting the Loki treatment thrown out the window. His initial velocity is 0. That's Tony's initial position. So that's y, because we're going vertical here. Y initial Tony. All right, yeah, so he's straight up there from rest, thrown out the window, falls, it's being accelerated by gravity. The Iron Man suit gets deployed 4 seconds later. So it actually starts its acceleration, its motion starts over here. And we're saying it starts from rest and then accelerates at a constant rate. So it's got a steeper parabolic curve. Because it's got a higher acceleration. And if you continued this parabola backwards, it would be something like that, right? But it starts, excuse me, it starts moving 4 seconds after Tony's thrown out of the building. And you could continue this curve down here. Anyway, they're going to intersect or meet right here. And this one's difficult because of the 4 second offset. All right, if you go back to question 9 with the basketballs, it's again 2 parabola, and so you can have a function to describe each parabola and solve that system of equations. So we have a function for Tony and a function quadratic function to describe the suit's motion. Right, just like with the basketballs in number 9. This is y initial right there of the suit S. Okay. And so the question's asking, does the suit get to him in time? All right, it leaves 4 seconds later after Tony does. It also takes 3.5 seconds to connect to him after it reaches him. So he actually only turns around like later in time, where he's going to be over here somewhere, because then it can activate and pull him up and away. So let's do velocity for these real quick. So Tony's got a 0 velocity and it's negative the whole time. I'm calling down the negative direction. And the suit starts at 0, but it starts speeding up faster and faster because it has a greater acceleration than Tony, which is how it's able to catch up. Right? So this is velocity in the y. It's a function of time. And then if we look at these velocity graphs, we can see Tony's going to have a constant negative acceleration, that's little g, and the suit has a constant negative acceleration, which is some number 30, I think. Is it? Yeah, so this would be minus 30 is actually what we would use because I'm calling down the negative direction. Okay, where did my screen just go? We just zoomed out a lot. All right, so here we go. Here we go. All right, so the trick with this one, and the reason why it's the hardest one, is to again think about where this intersection is going to occur, and you have to account for the time shift. There are other ways to kind of estimate it and still show that the suit can reach him, but the full thing you would want to be able to do is to show an equation that models the motion of Tony and an equation that models the motion of the suit, and they're both going to be quadratic equations. So you look at our parabola there, so we can see that. So like we had with our basketballs, we're going to have a y final position for Tony, which is going to be equal to, and we'll just write the full kinematic equation out, 1/2 acceleration in the y direction times time squared plus initial velocity in the y times time plus the initial position of Tony. All right, and then we have the suit. We'll have the final position of the suit, which is going to be the same as Tony because they collide, so to speak. They end up occupying the same position. 1/2 acceleration of the y direction, which is not going to be little g for the suit because the suit has the rockets burning. 30 meters per second squared plus y initial of the suit. All right, so the suit is what makes things weird because its parabola is shifted, is translated to the right along the time axis. And so that's how you can find the correct system of equations to write, or the correct equation for the suit is you think, okay, wait, what do you have to do to shift a parabola to the right along the time axis, or along the x-axis? I just mislabeled my y-axis here to y. All right, so with Tony, we'll go ahead and just kind of simplify things because we have an initial velocity of 0. So we have 1/2 of his acceleration. So that's going to be little g. It's minus 10, so it's going to be minus 5t squared, right? 1/2 of minus 10. His initial velocity is 0, so then we just need his initial position, which is 1300. All right, so there's once again an equation that models the behavior of our object, and it's got two unknowns, the final position and the time. The suit, this is where you're going to be like, meh, why? Again, its initial velocity is 0. It's going to go to 0. Its acceleration is 30, so half of that is 15, but it's also in the negative direction, so it's going to be minus 15t squared. But it's not going to be t squared because he doesn't have the same t as Tony. Okay, so you'd think we only get motion from the suit 4 seconds after Tony has left the building. So this, we need to modify the t, which this is how you translate the parabola to the right by an amount of 4 seconds, as you would do that. So, and you can make sense of this because you should have right here at 4 seconds exactly, at exactly 4 seconds, the position of the suit is still 1300 meters, right? And I have to have this little parameter in there. Otherwise, it's not going to tell me that the suit is still at 1,300 meters above the ground at the 4-second mark. It would tell me something else. Let's put in our last thing, which is the Y initial position of the suit. Right? If I put in T is 4 seconds for that, then I would get 0. This would be 0 plus the 1,300. And that would give me the correct position of the suit. That would be its current position Y at 4 seconds. It would have a position of 1,300. But that's only because I have this -4 in here. Okay, so I have to have that -4 to show that my suit has not left the building yet. At 4 seconds, it's still at 1,300. And that's something you learn in the algebra 2, right? Like shifting the graph over. All right, well, now you have two equations. We need a number in here for our initial position. It's 1,300. Okay, so you can, now it's a system of equations with two unknowns. You don't know your time and final position. You don't know your time. You don't know final position. But the final position of Tony will be equal to the final position of the suit. And so you can use that information to help solve your system of equations. You can set them both equal to each other, like I was saying before. So, well, this magic T minus 4 squared plus 1,300. Pardon me. Sorry. Okay, and then, so now you're just solving that. Or you can solve that system some other way, however you like. The time is roughly about 9 seconds, I think. I plotted it. I think we're still screen capturing this. All right, so see, these are the same equations that I wrote. Y1 in red is for Tony. So he starts at 0 seconds at 1,300 meters. And then Y2 in blue is the suit. So it starts at 4 seconds. It's at 1,300 meters. See? So that's where the suit starts its motion. This is just the rest of its parabola that we don't really care about. All right. So then it will intercept Tony here where they cross at 9.464 seconds, still 852 meters above the ground. And so that means you have another, 3.5 seconds is what I said for it to attach. So that's 3.5, so that's like, it'll be at 13 seconds when it attaches. So they'll be at 457.5 meters above the ground. And so that'll be when he can turn around and go back up. Okay, if the suit doesn't get there, then Tony would smack into the ground here. So these are the easy numbers to find out. You know, he's falling from rest, so you should be able to know he'll hit at 16.125 seconds if nothing saves him. And if the suit were to burn all the way to the ground, it would get there at 13.309. And that is another way you could talk about it having enough time to reach him. But these numbers here, these times are not sufficient to actually prove it totally. You would actually need to get this intersection. All right, so I forgot to include something. This video is the longest video of all time, and I was talking so fast, but I just do a lot. I did say I was going to say something about question 3. I don't know if I have the energy to actually edit this video. Okay, so there's a much easier way. No, not 3. Where's the intersecting carts? Okay, so there are other ways to solve this. It is important to understand this way that we're showing on the, hold on. It's important to know this way because you want to be able to model the position graph, model the motion of the carts with your equations of motion, and those are linear ones, so they're pretty easy. It's y equals mx plus b. Okay, the other thing you can do is check this out. Say we know they're going to hit somewhere over here, right? So let's say they collide here. That means the displacement of A, let's just say the distance A. Let's just say the distance. The distance A travels is going to be this right here. That'd be the distance A travels. And then let's make a different color. So then B would travel this distance. If that's where they collide, then the distance A travels plus the distance B travels will have to be what? Added together. Right, 12 meters. Okay, well, this one's traveling at 2.2 meters per second, but in the negative direction. This one's traveling at 1.4 meters per second, but in the positive direction. So their relative velocity is why I didn't do it with this. Relative velocity is like the velocity between them. So it's like when they collide, it's not like they're moving 2.2 or 1.4 meters per second. Their collision, they're colliding at a speed of 3.6. Like that's the speed it seems like they're colliding at. Because if you're watching something move towards you, and you're moving towards it at the same time, it looks like it's moving faster than it's actually moving, because you have a relative velocity. So here's a distance. Here's a relative velocity you could think of as a speed. Speed is distance over time. So we've got time is distance over speed. So the time is going to be 12 over 3.6. Ta-da! So I don't share that because that doesn't really teach you any of the stuff that we need to know. But there are, every now and then there's someone who is like, wait, can I just use the relative velocity and total distance? And it's like, yep, and you solve the problem super fast. All right, so now you know that. It was all of those questions I feel like looking at. I'm tired now. I will have to edit this video, render it, upload it. All right, everybody. That was fun. Good luck.